Okay, today's work we have a quick review of slope fields. If you remember from our AB class, when we did our slope fields, we did this worksheet, which ultimately the gist of this one was to take our points in question here, all these whole number points, and draw a slope field, which remember indicated kind of the general direction of what the solution curve would look like. The general strategy, just to review, is to take each of these points, whatever they may be. Let's just say for argument's sake we take the point 2, 1. And at point 2, 1, if we were to plug a 2 into this, we would get 2 plus 1, which would be 3. That means our derivative here would be 3. So at that point we would draw a line, a segment here that has a slope of 3. Now you'll notice that every point in this column is going to have the x value of 2, which means that we're going to have just a bunch of 3 slopes down here. And when we draw the 3 slope, remember, it doesn't have to be measured, it just needs to look positive from one thing and then look a little bit steeper than 1. And as we go to the right here, we can see that we're going to have a 4 slope at these points because these are all x equals 3. So we'll draw it a little steeper than we drew in this column. This column here is going to be 1, so that means we're going to draw slopes of 2 here. At 0, we're going to draw slopes of 1. At -1, we're going to draw slopes of 0. So we'd have horizontal line segments in all these spots. And then when we go on the other side here, when we put -2 in, we'd get -1, so we would draw slopes of -1 and so on. And so when we get done, we'll have a slope field. And when we take a look at the final product here, we might be looking at something like this. In fact, this looks exactly like the previous one, almost to the numbers. It's a little over to the left, I guess. But bottom line is this would be considered a slope field. And again, what this shows is it shows a family of functions whose derivative is whatever dy dx we were given. In this case, that would be 1/2 x squared. So any of these curves that could be drawn along this line would have the derivative here. Now, how would we indicate which one is the right one? Well, we need an initial condition. If we knew the initial condition was, let's say, x equals 2 or 0, y equals 2, then we would know that it goes through that point. We'd make a point there, and we would draw the curve essentially through that slope field, and it would mirror those slopes. All right. One thing besides being able to draw a slope field is to be able to match, like we did here. And again, you notice that when this one is got symmetry down the columns, all the columns have the exact same slopes. Okay, that's always going to be something that's just in terms of x. Okay. Likewise, when we have something that is in the rows that are exactly the same, then that only depends on y. And ultimately that would be choice D here, which would be dy dx equals y. And so this would be our slope field for that. Now, the more difficult part comes when we have x and y as part of our differential equation, because there's essentially no rhyme or reason to any of the different values. They're going to depend completely on what point we're at, not what different x value or a different y value. So to differentiate, though, to see which one of these is the right match for these, you can see that I have the answers on here, but bottom line is here, let's pick a point. So let's say we pick a point here, we'll go out to 3, 3, 1, we'll say, and this is our slope. We can see at 3, 1, we have a negative slope. If I were to put 3, 1 into this, I would have 3 minus 1, which would be 2. Now, does that look like it's a 2 slope? Of course not, it's negative. Okay? Whereas if I look at this one, if I do 3, 1 here, I'd have 3 over 1, but it would be negative. It looks like it's -3. That would match up. So we just want to pick a point or two and make sure that whatever point we're at, whatever point we've chosen, has the correct slope at that particular spot. Okay? So that's the matching part. And then again, the other thing that we did in AB is that when we drew a slope field, we were given an initial condition, and we had to draw the curve, essentially, that mirrors the slope field. Okay? Now, the question that we want to ask at this point is, why in the world would we need to draw a slope field? Well, if you remember the differential equations that we've been solving so far have all been solvable. They've all been equations that we can separate variables, we can find the antiderivatives, we can find c with the initial condition, and then we can solve for y. So all those have been solvable. Now the problem is that not all differential equations are solvable. So for instance, if we go back to number 17, as I mentioned, if we try to do this with separation of variables, it's not going to work. Okay? Our techniques that we do are not going to work, because if we added, we'd have y plus dy over here, and it would just ultimately would not be something that we could handle. Now, keep in mind that in college and so on, there are entire classes on differential equations. So it's not that we can't necessarily solve this, it's that with our techniques, we can't solve this. So this might be something that you'd learn later on. Okay? So the issue is then, if we do have a differential equation and we want to deal with the y that it came from, okay, then if we can't solve it with separation of variables, then we have no choice but to draw a slope field, because even at that point, if we were to pick an initial condition and have a curve that went something like that maybe, more like that I guess, we would at least, if we had a picture of the curve, we could use that y curve to make predictions. Okay? We could predict the y value at -1, at 2, at 3, and so on. And we could use that curve to make predictions, which is ultimately the whole purpose of solving a differential equation in the first place, is to get a y equation so that we can use it to answer whatever question that we're being asked. Okay? So that's a short review on slope fields. Let's take a look at this problem here. This is AB5 from 2008. And this is slope fields used to be a BC topic only, but now it's an AB topic as well. And so this is number 5 on 2008. So this is AB5. And this is a typical slope field problem that has been on the AP test of late. And there actually hasn't been one of these for a while. And in fact, I think this is the most recent one. But bottom line here is we have dy dx. And whether we can solve this with separation of variables or not is essentially irrelevant at this point. Bottom line is part of our points in this, and you don't generally get a whole lot of points for it, unfortunately. But we have to draw the slope field here on the points that are indicated, and you can see that the points indicated here are these 3 here, these 3, and these 3. And the and notice it says the 9 points indicated, so we don't need to do anything on the x-axis here. So with that said, if we draw our points, we have -1, and we get -1, 0. If I were to put a -1 here and a 0 here, we'd have -1/1, which would be -1. So we'd have that slope, and again I'm drawing a slope of -1 there at that point. And then if I go -1, 1, if I were to put again a -1 in here, I'd get 1. If I put a 1 in here, I'd get 0. And so at that particular point I would have a 0 slope, so I should have a horizontal segment there. And then if I put in -1, 2, -1 here again will give me 1, 2 in here will give me 1, so I'd have 1/1, and that would be, of course, +1. So those are my 3 slopes at that point. And then on the other side, they've asked it to do the same thing with these points, so 1, 0. 1 in here, of course, is 1, and 0 in here would be -1, so I'd have a slope of -1 there. At that point, 1, 1, I'd get 0 on top, 1 on the bottom, so I'd get horizontal again. And then up here at 1, 2, I would have 1 in here, 1 in here, so I would get a slope of 1 there also, so these two should be the same. And then finally, if I do my 2, 0, if I put my x equals 2 in here, I'd get 4, -1/4, so that would be significantly less steep because it's -1/4. If I put 2, 1 in here, 1 minus 1, that's going to be 0 again, so all 0 slopes along that point. And then finally 2, 2, I'd get 2 minus 1, which is 1. 2 squared on the bottom is 4, and I'd get +1/4 here. So again, significantly less steep is how we want to draw it. So again, is there any perfection or any measurement in terms of drawing the actual slopes here? No. But bottom line is we just need to make sure that they are approximately the slopes that were given if we put the particular point in this differential equation. So that right there would be our slope field, and we'd be done. So you have some problems today to work on from your slope field section here in section 7.1. So good luck.